If solid-state batteries are truly the future, why are they already spinning wheels on two-wheeled machines while four-wheeled electric vehicles are still waiting? Donut Lab's motorcycle demonstrations are not a PR stunt. They are a carefully chosen battlefield. The real question is not why haven't EVs adopted solid-state batteries yet, but rather why do solid-state batteries suddenly make sense on motorcycles, while remaining fundamentally incompatible with mass-market electric cars today? Let's deep dive into this episode today and become our first subscribers for the channel. Thank you, fellas. The first key reason solid-state batteries feel at home on motorcycles is scale. A typical electric motorcycle operates with a battery pack well below 10 kilowatt-hour, often closer to 4-8 kilowatt-hour for performance-oriented designs. From a manufacturing standpoint, this is an entirely different universe compared to electric cars, which routinely require 60-100 kilowatt-hour packs. Why does this matter? Every solid-state cell today still suffers from yield sensitivity, microscopic defects in solid electrolytes, uneven interfaces, or slight thickness variations can render a cell unusable. When you manufacture a small pack with fewer cells and smaller surface areas, your statistical exposure to defects drops dramatically. In engineering terms, the probability of catastrophic failure scales non-linearly with size. This leads to a hook-worthy question: if solid-state batteries fail at large scale, why not start small, where physics is more forgiving? On motorcycles, Donut Lab can afford to select cells with tighter tolerances, scrap defective units without destroying margins, and maintain quality control that would be economically impossible for a 100 kilowatt-hour automotive pack. A defect rate of even 1% may be survivable in a 6 kilowatt-hour system, but it becomes devastating when multiplied across hundreds of large-format cells in an EV. Weight is the second decisive factor, and here motorcycles play directly into solid-state batteries' strongest advantage. On a motorcycle, every kilogram matters. Acceleration, handling, braking, and even rider fatigue are all directly affected by mass. Traditional lithium-ion packs, especially those optimized for safety and longevity, carry a heavy burden of inactive materials, liquid electrolyte, separators, thermal buffers, and rigid enclosures. Solid-state batteries remove or reduce many of these components. Even a modest 20–30% gravimetric improvement can translate into tens of kilograms saved on a bike, which is transformative for performance. This raises another question that keeps viewers watching. Why does a 20% weight reduction matter more on motorcycles than on cars? The answer is leverage. Removing 20 kilograms from a 200-kilogram motorcycle is a 10% mass reduction. Removing 20 kilograms from a 2000 kilograms car is barely noticeable. Engineers think in ratios, not absolutes. And solid-state batteries offer their highest leverage precisely where vehicles are smallest. Thermal management is another often overlooked reason motorcycles are a natural entry point. Electric cars rely on complex liquid cooling systems to manage heat during fast charging and high-power operation. Solid-state batteries, despite being safer in terms of flammability, are not immune to heat. In fact, many solid electrolytes suffer from reduced ionic conductivity at lower temperatures and mechanical stress at higher temperatures. Managing this across a massive automotive pack requires sophisticated thermal uniformity, which remains a major unsolved challenge. Motorcycles, however, benefit from a simpler reality. Their battery packs are smaller, their power demands are intermittent, and their surface area to volume ratio is far higher. Airflow does much of the thermal work for free. This naturally prompts the question if solid-state batteries hate thermal gradients. Why force them into giant EV packs when motorcycles let them breathe? From an engineering standpoint, this is not a compromise, it is optimization. Cost, inevitably, is where the conversation turns uncomfortable for EV advocates. Solid-state batteries today are expensive, often several times the cost per kilowatt-hour of conventional lithium-ion cells. For a car, this would mean adding tens of thousands of dollars to the sticker price. But motorcycles live in a different market psychology. High-end electric motorcycles already target enthusiasts who accept premium pricing in exchange for performance, exclusivity, and cutting-edge tech. A $2,000,4,000 battery cost increase is painful, but survivable in this segment. A $20,000 increase on a family EV is not. This leads to a critical economic hook: is solid-state battery adoption being blocked by technology or by consumers' unwillingness to pay on motorcycles? Donut Lab bypasses this trap entirely. The product does not need to be mass-market cheap. It needs to be technologically impressive and functionally superior. In engineering economics, this is known as a beachhead market. But once we shift our gaze back to electric cars, the barriers reappear taller and harder. Scalability is the single biggest obstacle. Producing solid-state cells at automotive scale means fabricating large-area solid electrolytes with near-perfect uniformity. Even microcracks invisible to standard inspection can become failure points under repeated charge-discharge cycles. As cell size increases, internal stress accumulates, especially during lithium plating and stripping. In small cells, this stress is manageable. In large cells, it becomes destructive. This raises a troubling question for EV timelines if dendrites can still form in solid electrolytes at scale. What happens inside a 100 kilowatt-hour pack after 1000 cycles? Laboratory data shows that while some solid electrolytes suppress dendrite growth, they do not eliminate it entirely. Mechanical fractures open pathways for lithium penetration, leading to internal short circuits. In a motorcycle, such failures are easier to detect, isolate, and mitigate. In an EV, they are exponentially harder to control. Manufacturing cost compounds the issue. Solid-state production requires new equipment, new materials, and entirely new process flows. Existing lithium-ion gigafactories cannot simply be upgraded. This means massive capital expenditure before economies of scale can even begin. For automakers already struggling with EV margins, this is a terrifying proposition. The supply chain for solid electrolytes, sulfides, oxides, or polymers is still immature, fragmented, and vulnerable to bottlenecks. So where does Donut Lab fit into this picture? Their strategy appears less like a shortcut and more like a controlled experiment. By designing solid-state batteries specifically around motorcycle architectures, they minimize mechanical stress, reduce cell size, simplify cooling, and limit economic risk. This is not a stepping stone in the traditional sense. It is a parallel path. However, the data gathered from real-world motorcycle use cycle life, degradation patterns, thermal behavior feeds directly into future automotive designs. The final question viewers inevitably ask is about timing. When will the gap between motorcycles and cars finally close, based on current materials science progress, manufacturing trends, and pilot-scale production data? A realistic window for meaningful automotive solid-state adoption sits between 2028 and 2030. Before you leave, please help us reach our first channel subscribers, and don't forget to click that bell icon to quickly receive notifications about upcoming exciting content. Thank you, fellas.